All right, so welcome to the 14th lecture for STAT 313. So today we'll be starting a new chapter, that's chapter 8. And here we'll be studying the optimal test of hypothesis. Okay, so let's get started. All right, so what we study at the very beginning is the so-called most powerful tests. And in the next section, we'll be studying uniformly most powerful tests. Okay. Now, before going in details of this section, I would definitely encourage you to revise the concepts from chapter 4. That means the first chapter that we studied, because this will be very useful here. Like you should be able to identify what I mean by the hypothesis testing, what I mean by, say, the type 1 error, type 2 error, and then a power of a test. Okay, so all those things should be very clear. Okay, now let's see. Let's first consider an example. Okay, so this example will be clarifying what we are going to do next. So this is the following example. It goes like this: consider a random experiment, or consider the random variable x that has a binomial distribution with parameters with n equals to 5 and p equals to theta. Okay. So let f of x theta denote the PMF, the probability mass function of x. Okay. So suppose we are considering the null hypothesis H0 is theta equals to 1/2, and versus the alternative hypothesis H1 is theta equals to 3/4. Okay. Now let's see. So we are testing this theta equals to 1/2 against theta equals to 1/4. So now the following table gives you all this probability. I can always compute, say, for example, what is f of, say, x, and then if theta equals to 1/2, that what is that? So my n is 5. So it's 5 choose x times 1/2 to the x, and then 1/2 to the 1 minus 1/2, that is 1/2 to the 5 minus x. So which is 5 choose x, 1/2 to the 5, right? So that is the probability mass function for theta equals to 1/2. And the probability mass function for theta equals to 3/4 would be 5 choose x, 3/4 to the x, 1/4 to the 5 minus x, right? So these are the two numbers. Okay. Now suppose I'm writing this x values 0, 1, 2, 3, 4, and 5. 0, 1, 2, 3, 4, and 5. So those are the possible values of x, right? 0, 1, 2, 3, 4, 5. Okay. If I compute this f of x 1/2, that means for theta equals to 1/2, the numbers are 1/32, 5/32, 10/32, then 10/32, 5/32, and 1/32. So those are the values of the probability mass function for theta equals to 1/2, when the true value of theta is 1/2. Okay. What about for the other case, f of 3/4? I have the formula right here. So all you have to do, you have to put the various values of x. So the first one is going to be 1 over, well, uh, so it's 1 over 1024. Then it's 15 over 1024. Then it's 90 over 1024. Then it will be 10 over 1024. Then it'll be, sorry, 90 over 1024, and then this is going to be 270. Sorry, it's 270. Okay. And then it's 405 over 1024. And finally, it's 243 over 1024. Okay. All right. Okay. If you add everything here, it's 1, and it's 1 here. Okay. Now, let's see. So we are trying to test this hypothesis, theta equals to 1/2, against this one. Okay. So let's first assign the significance level. So let us consider, for this test, consider a significance level to be alpha equals to 1 over 32. Okay. Now, what is the goal here? So goal, we want to find the best critical region of size equals to 1 over 32. So that is what we are trying to find. So a best critical region of size 1 over 32. What does it mean? So there may be a bunch of critical regions of size of this one. So if you recall, what is the critical region? So basically, the size of the critical region or the significance level is given by the probability of type 1 error. So that is basically we are rejecting a null hypothesis when it's true. Okay, so that is the region size. So we are saying that okay, so there may be various critical regions of this size. Now, what is the best way of understanding the critical regions? Okay, what I mean by that will be clear pretty soon. It may be very confusing at this point, but why there will be more than one critical region? Let's see with this example. Okay, so let's see. I'll explain everything in terms of this example. Okay, let's look at this example. So suppose I denote two events. So one is say A1. So that's one of my sets, which is given by x such that x equals to 0. And my A2 is x such that x equals to 5. Okay. So then with the null hypothesis, so if the null hypothesis is true, that means if your theta is really 1/2, then what is the probability of this region of this A1? It's 1 over 32, right? And what is the probability of A2? That is also 1 over 32. So if we define that getting a 0 or getting a 5 is a critical region, so then both of these will have a size of 1 over 32, right? So that means suppose we design a test. We are saying that, okay, so if we get, so the critical region is 1 over 32. So the critical region is given by 1/32. So is that, both of these are having size of 1/32. Now, should we use the region when getting a 0 is rejecting the null hypothesis, or should we use the critical region, which is the same size, where getting a 5 is rejecting the null hypothesis? So the question is, when can we reject the null hypothesis? When we are getting x equals to 0 or x equals to 5? They have the same type 1 error. Okay. So let's try to answer this question. We'll see that one will make much more sense than the other one. Okay. Observe. So observation 1. Observe that what I just said. Probability of theta equals to 1/2. And then if I have x in A1, which is same as A1 is this one, x equals to 0. So it's same as probability of x equals to 0, which is equals to 1/32, as well as the other probability of theta equals to 1/2, x in A2, which is probability of x equals to 5, is 1/32. They're same. Okay. Remember, H0 is theta equals to 1/2. So under the null hypothesis, I can choose this A1 and A2. Both are a possibility of choosing as a critical regions. Okay. Suppose we are rejecting the null hypothesis if this suppose the critical region is A1. So that means if we are having if we are getting a value here, we are rejecting the null hypothesis. Or we have another possibility, A2. If we are getting a value here, then we can reject the null hypothesis. Okay. They have two possibilities. Okay. Also observe that, observation 2, there is no other subset A3 of the space X such that X equals to 0, 1, 2, 3, 4, 5, such that probability of X in A3 under the null hypothesis, meaning theta equals to 1/2, is equal to 1/32. There is no other. Okay. So that's pretty much it. Okay. Now, so if we want to study a best, so there are two critical regions of size. So there are two critical regions, namely A1 and A2. Of size, which is alpha, equals to 1/32. Now here is a question. What can be, question, what can be a best critical region? The question is not well formulated yet because I don't even know what is meant by this best, but we'll try to see this with an example. And by the way, best critical region compared to H0 and H1, okay? For testing, H0 against H1. Okay. Because every time I change the hypothesis, it changes. Okay. Okay. Let's look at this one. So let's let's see. What about probability of theta equals to observation 3? let's consider the alternative hypothesis. H1 was what? So H1 was the alternate hypothesis, which is theta equals to 3/4. So if with respect to that, let's see what is the value that x is in A1. Okay. This looks very odd, but it's something very simple. So it's basically probability of the theta equals 3/4, x equals to 0, right? And we have that right here, this number, right? So 0 and 1 over, so it's 1 over 1024. So this number is 1 over 1024. We found it. Okay. Now we are in a problem. Also observe that probability of theta equals to 1/4. X in A4, A2 is same as theta equals to, 0/4, x equals to 5. And this number is really 243 over 1024. Okay. Now we have all the information and try to see what I mean by that. Okay. Now here is a scenario. So observation, and this is the most important observation. So if A1 is chosen as the critical region, then probability of we reject H0 given H1 is true. What does it mean? So H1 is true, and we are rejecting the null hypothesis. So what is that? So that means when so basically this is given by this number. So we are using the H1 theta, and the critical region is used. So this is A1, right? So when x is in A1, so that's the critical region. So we are rejecting the null hypothesis under the assumption that H1 is true. So what is that? It's 1 over 1024. However, probability of rejecting H0 when H1 is true. So now, so that means x should be in A1, but also, sorry, H0 is true. So x should be in A1, and I'll be using theta equals to 1/2 for computation. So it's right here. So x is in A1, and I'm using the null hypothesis for computation of this probability. It's 1 over 32, right? So this is going to be 1 over 32. Now, isn't it sort of meaningless? So we are, when H0 is true, we are rejecting H0 with the probability 1 over 32, which is pretty high, compared to when H1 is true, we are rejecting H0 with much lesser probability. Okay. So honestly, what we really expect is when H1 is true, so we want to reject H0 with more probability, right? Because the other one is true. So of course, we should be rejecting this one. So when H1 is given to be true, I should be rejecting this with high probability. So this number should be higher. And if H0 is true, I should not reject H0. So this should be lower. So this should be lower, and this should be higher. So what we got here is counterintuitive, and actually it's ambiguous. I mean, we cannot really use this as a critical region because it's something meaningless. It's basically shows absurd results, probabilities. Okay, versus my last observation. So observation 4 or observation 5. Let's now use the probability if A2 is chosen as the critical region. then probability of rejecting H0 when H1 is true. What is that? So my A2 is chosen as a critical region. So my X is in A2 under the probability of H1. So X is in A2 under the probability of H1. So that is 243 over 1024 versus probability of rejecting H0 when H0 is true. That should be less. So that means my X should be in A2 under the theta equals to 1/2. So theta equals to 1/2 H0. X should be in, so it's in 1 over 32, right? Okay. Okay, so this is more meaningful. So if H1 is true, I should reject H0, and if H0 is true, I should not reject H0. Okay, so this number is actually, if you compute this, so basically what we have is, so if I just compute these numbers, I have this one is 0.2373, which is higher than 0.0312, which is lower. Okay, so of course, this is more meaningful. So if I give you two options, the options are summary. So if two options for critical region, in this case, A1 and A2, we choose A2 as it is meaningful. A1 gives some absurd results. Okay. Another way of saying this is we say A2 is the best critical region for this test. Remember that the critical region is always designed for a particular test. So for the test H0, theta equals to 1/2 versus H1, theta equals to 3 over 4. Okay. Final observation, note that in this case, for the best critical region, we also have the following. So if I compute probability of theta equals to 3 over 4 of X in A2, which is what? So basically this is probability of theta equals to 3 over 4. X in A2 means X equals to 5. What is this number? So we have already found this number. So this number is right here. Theta, so X equals to 5, theta, so it's 243 over 1024, right? So let's write it here, 243 over 1024. And I'll write the other one here. So probability of theta equals to 3 over 4, X in A1. Okay. So that means this is really probability of X equals to 0. And what is this number? So X equals to 0 under theta equals to 3 over 4. So I go to this table and I check this number. It's 1 over 1024. So of course, from this, you see this is bigger, right? So my point is this quantity is bigger than this one. Okay. Note this, because now I'll formalize this in a definition. So we see that for best critical region, so we say that A2 is the best, right? So if A2 is the best, then probability under the alternative hypothesis. So this theta equals to 3/4 is under the H1, right? Under the H1, that X is in A2 is bigger than under the H1, X is in A1. Okay. So what are the similarities? The similarities are right here. Similarities are, so for both, so I think I wrote it right here. For both 0 and 5, for X equals to 0 and X equals to 5. So my critical region for like under the null hypothesis, getting 0 and getting 5, they are equal probable, right? So that's what we wrote here. That's our first condition. The second, so we need that for being a candidate of the critical region, but then we must check the other one. So I have to check for theta equals to 3/4. Which one is true? If one is more than the other one, whichever is more, that is the best critical region. Okay. Now we didn't prove it yet, but so this is there is a way to formalize it. I'll do it very soon. But let me just write the definition here. Okay. So I'm now ready to write the definition. Definition with this motivation. With this motivation, let's write the definition of the best critical region. Now this goes like the following. So it goes as, let C denote a subset of the sample space. Then we say C is the best critical region of size alpha for testing the simple null hypothesis H0 such that theta is theta prime against another simple alternative hypothesis, against the alternative simple means it's of the form equal, right? Simple hypothesis H1, which is theta equals to theta double prime, if part 1, I want under the null hypothesis, that is with respect to theta prime, X in C should be alpha. Note that. So that is the first condition. So these two are possible candidates. So A1 and A2, because under the null hypothesis, that is equal to that is equal to alpha, right? So we set alpha to be 1/32. So these two are the possible candidates, right? That is the first one. But the second one is, and for every subset A of the sample space, I must have if theta prime X in A. So that means what? So that is A is another candidate, another possible candidate of being the best equals to alpha. So for every subset A of the sample space, so that this is true, like you can think about like here, the A2 was the best region, right? But A1, for A1, we had the same result. So the A1 is a possible candidate. So in this case, C was like A2, and what I wrote as A is like A1. Okay. What do we have? We have the last result that I wrote here. So I wrote this one, right? So I'll be writing this one here. So I'll write that with respect to the alternative hypothesis, theta prime, theta double prime, x in C, so is bigger than P of theta double prime, x in A. Note that, I mean, it may be very abstract, but if you look at this one, it makes a lot of sense. So this is the best region. So with respect to the alternative hypothesis, so the best one, its probability should be more than the other ones, right? So then A would not be the best. Okay. So A was a candidate for being the best by the virtue of this one, but it's not the best. So if this is true, okay. All right. So another way of writing this is the, so I mean, if you recall this one, so this is probability of rejecting the null hypothesis um, with respect to when the alternative hypothesis is true. So basically, this is the power of the test, right? The test associated with C is at least, I think, let me just rewrite equal, bigger than equal to. In general, it should be bigger than equal to. At least as great as the power of the test. So this is the power of the test associated with C, right? So this is power of the test associated with C is at least as great as the power of the test as the power of the test associated with every other A. Okay, so that is the formal definition. Now see that this is a lot of computation. So what we did in the previous example, there's a very simple definition, but I mean, how do you know which one is the best one? Like for every possible problem, we cannot just go back and compute all these things. And this may be very, I mean, technical, and it may take a long time, right? So there are ways for doing this. So here is a way for doing this. In practice, and this is done by the famous Neyman-Pearson theorem. So theorem. So this theorem will provide a systematic way, a systematic method of determining a best critical region. Okay. And that will be captured in this theorem. Okay. So I'll first provide this theorem, and then we'll go back and we'll study the previous example, and we'll see how it makes sense. This is a beautiful theorem, which is, and I also encourage you to read the proof from the book. I will not do the proof. The proof is very easy, and it's very simple, and you should be able to follow it. So it's Neyman-Pearson theorem. Okay. It goes like this: let x1, x2, xn, where n is a fixed positive integer. Integer denote a random sample from a distribution that has PDF or PMF given by, say, f of x theta. So that is pretty much we are doing, right? So we are drawing from a random sample. So these are IIDs, and then they're following a distribution which is PDF or PMF f of x theta. Then the likelihood of x1, x2, xn is given by L of theta, which is the product of I from 1 to n, f of xi theta, right? We all know this. There's nothing new. Now the new part. Let theta prime and theta double prime be distinct fixed values of theta so that omega is theta such that theta can be either theta prime or theta double prime. So my possibilities for the values of theta are two, theta prime and theta double prime. There is no third one. Okay. Why I'm saying this? Because later on we'll see that we'll be making this more general. So there we can have more values. But here we have two options. So the value of theta can either be theta prime or theta double prime. Okay. Let k be a positive number. It's very important. So k is positive number. Okay. Now suppose that C be a subset of the sample space so this is the subset of the sample space such that the following three conditions are true. So I have now a region C. Eventually, we will be calling this a best region. So the first one is number one is L of theta prime over L of theta double prime is less than K for each X in C. Please note that this X can be multidimensional. So I'm just using this as a scalar here, but this X can also be a vector. So basically X is a value. So this is a value of X1, X2, Xn. Okay. And C is in the, so it's also an n-dimensional space. Okay. It's just like the critical region. Okay. Part B. L of theta prime of L of theta double prime is bigger than or equal to K for each X in the complement of C. We'll do an example, so don't worry about this one. So as long as you're in the critical region, so this number is strictly less than 1, strictly less than K. Sorry, this number is less than or equal to K. As long as you're outside the critical region, then this number is more than or equal to K. Okay. And finally, in order to be the critical region, or the best critical region, I must have probability of under the H0. So X is in C is equal to alpha. Okay, so where this x is x1, x2, xn. Okay, so basically this C is a subset of the sample space, so that this is true. So basically you have seen this before when we define the critical region. Okay, depending on the context, we'll not be using it that much. So this x can sometimes be written as a row vector, sometimes as a column vector. Okay, now what happens if this is true? Then here is a conclusion, the part of the theorem. Then C, for which this is true, this C is a best critical region of size alpha for testing the hypothesis H0, which is theta equals to theta prime, against H1, which is theta equals to theta double prime. That's the conclusion. Okay? So if these three conditions hold, meaning that if we have L of theta prime, if you can figure out a constant k or positive number k, so that this ratio theta prime over theta double prime is always smaller than or equal to k for a particular critical region, and it's bigger than or equal to k for the complement of the critical region, and the size of the critical region is alpha. So then we say that the C is the best critical region of size alpha, and that's why actually this is needed. So this is directly related to this one. For this hypothesis testing. Okay, so now there are a lot of words, but we can make it work, and we can see this with examples pretty easily. Okay, so let's see if we can understand this. So let's see how this ratio actually makes sense. Let's do the example, the first one. Say, so this is an example, and from the exercise 8.1.1. And it goes like this. In fact, it's a follow-up with one of the examples that we did not do. So let me just first do that example. Okay, so let's consider the other example and then we'll go. So here, let x equals x1, x2, xn denote a random sample from the distribution that has a PDF f of x theta equals 1 over square root of 2 pi e to the power of minus x minus theta squared over 2 for minus infinity less than x less than infinity. Okay. So we want to test. So we want to test the null hypothesis, the simple hypothesis H0, which is theta equals to theta prime, which is equal to 0, against the alternative simple hypothesis. So this is my null hypothesis, which is simple one because it's equality. Alternative simple hypothesis. Say H1, which is theta equals to theta prime, double prime is 1. So theta prime is 0. So basically, we are trying to see if theta equals to 0 or theta equals to 1. Okay. Okay. Let's compute this. So we'll be using this Neyman-Pearson theorem. So let's compute this ratio. Okay. So basically, if we can figure out a constant k, then we are done. So let's consider L of theta prime over L of theta double prime. So we want, so if I did that, so let's see. This is a likelihood function. So that's a product of n of this when theta prime equals to 0, right? So the value of theta is 0, and I'm multiplying n of those. So I have 1 over square root of 2 pi to the power of n. And I have multiplied, so theta equals to 0, I'm assuming. So if we are multiplying n of those, so it's e to the minus summation I from 1 to n xi squared over 2. Okay, so that's the numerator. For denominator, my theta double prime is 1. So I'm adding up 1 over 2 pi to the nth power e to the minus summation I from 1 to n xi minus 1 squared over 2. Okay, so this and this cancels. So what we have here is basically, so this quantity is really e to the power of, if you simplify, so there is xi squared that got cancelled, and then we have the term, so the last term is n over 2, and then we have two terms, right? So it's 2xi, so it's basically the 2 cancels with this 2. So what we have is e to the minus so e to the minus I from 1 to n xi plus n over 2. Okay, so that is the quotient. Now, if k bigger than 0, and if I want to implement the theorem, the set of all points x1, x2, xn such that I want this L of theta prime over L of theta double prime. So remember the previous theorem. So what do we want it? We want this to be less than k. And this will be then is a best critical region by the last theorem, right? By the Neyman-Pearson theorem. Okay. So the set of all points so that this quantity is less than or equal to k, so that would be a best critical region. Now, this is the fact. Okay. Once again, so k is bigger than 0, and this is true. So whatever x1, x2, xn that satisfies it, look at this one. So we say that so this is x in C. So that means x1, x2, xn in C. So whenever this is true, we call that to be that C is the best critical region, right? So if you compare that. Now, let's massage that a little bit in the sense that what do we have? So this quantity means e to the minus I from 1 to n xi plus n over 2 less than k. Okay. So for all x1, x2, xn, for this is satisfied, it's called the best critical region. So that means if I take the log and if I simplify, so that means I have I from 1 to n, xi plus n over 2 is less than log of k. So that means I from 1 to n xi, if I multiply, so it's bigger than uh, minus n over 2, so n over 2 minus log of k. Okay. So this is the best critical region, right? Now, this is a constant. So this constant, I can call it C. Okay. So the best critical region, a best critical region is C, where this x1, x2, xn that satisfies summation I from 1 to n. I'm writing this one is C with a bigger than sign. So xi is bigger than equal to C, where C is a constant. Can be used to determine the sign, to determine the size of the critical region. Okay. That is alpha. We'll see how it's done. Okay. Okay. So now before going further, so let's see. In this case, if I consider the random variables xi, so this quantity is given by I from 1 to n, xi bigger than c, right? If I divide by 1 over n, so that means what I have is x bar is really bigger than equal to some C1. Let's call this C1. Okay. So then, so that basically I can test. So we can test the best critical region, test a best critical region based on, we don't really need all those x1, x2, xn. So based on the statistic x bar, that's pretty much it. Okay. So so that is the conclusion. So that is if H0 is true, so if H0 happens to be true, that is theta equals to 0, then X bar really satisfies a normal distribution with mean 0 and variance sigma was 1. In this case, we look at the structure for all the x's. So x in this case was given by the normal. It's a standard normal distribution. So that means it's mean. So x for x1, x2, xn. Each of those cases, it has mean 0 and variance 1. So for x bar, it will have mean 0 and variance sigma squared over n. So that means sigma squared is 1. So it's 1 over n, right? So this has X bar will be following a normal distribution. Okay. So probability of X bar so bigger than equal to C C1, we want to be equals to alpha. So this is what we want. Okay. And that is basically the test. Note that what we did. So basically, we want this to be satisfied for being the best critical region. So this is, let's write, say B1. And then we transform this B1 to B2. So in order to in order to have a best critical region, so X bar must satisfy this one. Okay. Now, if I want us this will be satisfied, and I mean, so this is the critical region. So in that region, I'll be rejecting the null hypothesis. So the probability of this critical region is so the probability of the critical region is called the size of the critical region, and that is alpha. That is something we want, right? So this is, let's write B3. Okay. Now we are almost done. So with this, we can say that, so here is the machinery. So here is the procedure. So the procedure is if the experimental values of x1, x2, xn are, say, little x1, x2, xn, compute little x bar equals to 1 over n, I from 1 to n, xi. If x bar is bigger than c1, then the hypothesis h0, which is theta equals to 0, would be rejected at the significance level alpha, which is already set up. Okay. If x bar is less than c1, h0 would be accepted. That's it. So this is the total procedure that we built based on this one. So what is an additional thing? So this, this critical region that we defined here is actually a best critical region. So this critical region, as shown, is a best critical region. So maybe you have seen this test before, but the fact that this is the best critical region, so now we understand it. Okay. At this point, we are ready to move to the example that I was about to start. So let's do this one. So here is an example. So this is exercise 8.1.1. Okay. Okay. Let the simple hypothesis in the last example read h0 theta equals to 0 and h1 versus h1 is theta equals to -1. Last time it was 0 versus I believe 0 versus 1, but now it's 0 versus -1. Show that the important thing is here the best test best test. So it really means with respect to the best critical region. Okay. So that show that the best test of H0 against H1 may be carried out by the use of statistic X bar. And that if n equals 25 and alpha equals to 0.05, the power of the test is 0.9996 when H1 is true. Okay. Let's show it. Okay. So here's the solution. Just like before. So I'll be basically copying mostly from the last problem. So we had this theta prime over theta prime, theta double prime. So this is in our case 0. This is and now it's -1, right? So just like before, L of theta prime, which is equal to 0 over L of theta double prime, which is equal to -1. So this is going to be equal to the computation will be, so here it's the 0, but this becomes +1. So that +1 would go here. So it makes it a +1 here. So that's the only difference, right? So we have a +1 here. So the only difference between these two is I'll now have a +1. Okay. So let's write it down. So it's e to the plus xi, I from 1 to n plus n over 2. That's the only difference. Okay. So now, just like before, if L of 0, let's write this as 0, L of -1 is less than k for k bigger than 0, that would mean e to the summation xi, I from 1 to n plus n over 2 less than k, right? Which means summation, if I take the logarithm, I from 1 to n, xi plus n over 2 is less than log of k. Okay. So basically I have I from 1 to n xi is bigger than, is less than log of k minus n over 2. Okay, let's call this one to be C. So a best critical region is C. I'm just copying from the last problem. So it's x1, x2, xn, such that summation I from 1 to n xi is less than C. Last time it was bigger than C, now it's bigger than C. It's less than C. Okay, and this C constant can be used to determine the significance level of the region. Okay, now observe that in this case, so that means we have I from 1 to n xi less than C. So if I divide by n, so that means I have little x bar, I'm just working the sample, is less than equal to, say, C1. In our, I mean, if we just use the By the way, so this is my B1, the first equation for the critical region. This is my conversion to the next one, B2. Just if you just compared the last problem. Okay. So that means we have shown that hence the best test. Why best test? According to the NP theorem by Neyman-Pearson theorem. So this is by Neyman-Pearson theorem for best critical region. Okay. We need this, right? So the best test, so what we found is, therefore, the best test may be carried out by the use of X bar. Okay. That's it. So because we used here X bar. So that is the first part. Now, so basically this region is same as this one, and the best test can be carried out this way. Now the second part is more interesting. It says that when n equals to 25 and alpha equals to 0.05. Now let's see, X bar under X0, under H0, null hypothesis. So it follows so under X follows a normal distribution. It mean zero variance one, right? So X bar, so it's say X1 follows. So X bar is given by normal 0, 1 over how many samples are there? So n is 25, so it's 25, right? So variance was 1, so it's 1 over 25. Therefore, I want a significance level of alpha is 0.05, so 0.05, hence, which is really equal to probability under H0, my X bar is less than equal to C1, right? Now, let's try to make use of the fact that X bar is a normal with this. So I can divide by the, so let's write this P of H0. Under H0, it follows a normal distribution. So it's X bar minus 0 over its variance over sigma is 1 over square root of 25. So it's less than C1 minus 0 over 1 over square root of 25, right? So that means probability of H0, and this is basically Z. It's a standard normal distribution, is less than, this is 5C1. And so this Z less than 5C1 is the CDF of 5C1. So we want the equation becomes 0.05 equals to phi of C1. So from the table, we can find that 5 of C1 is really minus 1.645. So that means C1 equals to minus 0.329. Okay. So that's the value of C1. Okay. So this is how the value of C1 is generated. So we found this one. So now let's see what we can do with this one. So the second part is saying that show that the power of the test is 0.9996 when H1 is true, right? So now the power of the test is really probability under H1 rejecting the null hypothesis. So that means note that what we have. So we want to have the probability of rejecting the null hypothesis. So which is probability of, so it's basically probability of X bar is less than C1 under H1, and we found C1 to be less than minus 0.329 under the alternative hypothesis. So under H1, we know that X1, X2, etc., they follow normal with mean -1, variance 1. That's what's given, right? So that means I can write this as probability of X bar. I can subtract -1, so it becomes +1 over the sample variance is still 1 over 25. So it's the square root of 1 over 25 for the X bar. Yep. So this really means X bar follows normal with -1, 1 over 25. X 25. Okay, so this is less than equal to minus 0.329 plus 1 over 1 over 25. So this is, if you simplify it, this is nothing but Z under H1. And this number is 3.355. So this is really phi of 3.355. And if you check it from the table, it's 0.9996. So the power of the test is really this one. So note that you cannot just find the power of the test immediately. So you need the C1, right? And for finding the C1, you have to go through all these processes. Okay. So this is a very nice way of computing a power of the test for a particular case. Now, let's do one more example, which is based off this one. And we're studying this as example from exercise 8.1.2. It goes like this. Let X is a random variable. Let X be a random variable, which has the X, the random variable X, have the PDF f of X theta, which is 1 over theta e to the minus X over theta, 0 less than X less than infinity, and 0 elsewhere. So that means it's an exponential distribution. Consider the simple hypothesis theta H0, which is theta 2, and the alternative hypothesis, which is also a simple hypothesis, theta double prime, which is 4. Let X1 and X2 denote a random sample of size 2 from this distribution. Okay? Show that the best test of H0 against H1 may be carried out by the use of the statistic, and the keyword is best test, statistic x1 plus x2. Okay, so this is another example of finding a best test. Okay, solution will be very similar to what we have done before. So I'll start by writing L of theta prime, which is 2, over L of theta double prime, which is 4. Let's compute this. Okay, so this is going to be, well, so this is, so it's a sample of size 2. So here it's basically 1 over theta prime squared e to the minus x1 plus x2 over theta prime over 1 over theta double prime squared, and then I'll plug in the value, of course, e to the minus x1 plus x2 over theta double prime, right? So this is the test statistic. So which is same as if I compute these numbers. So basically theta double prime is 4. So it's basically 16 over 4. And then we have e to the minus x1 plus x2 over theta prime, which is 2 times e to the plus x1 plus x2 over 4. That is this. So that is 4 times. I'll not simplify it. So it's let's write this way: x1 plus x2 over 2 e to the x1 plus x2 over 4. So that is my quotient. Okay. What do you want? So by the Neyman Pearson theorem, we want for best test what do you want? We want L of 2 over L of 4 to be less than equal to k for some k bigger than 0. Okay. So let's simplify this. So what it gives me is the following. I think my page number is wrong. So this should be 11. So what it gives me is the following. So if I take the logarithm, so I have the logarithm of, so log of 4 minus x1 plus x2 over 2 plus x1 plus x2 over 4 should be less than log k by taking the logarithm. So what we have is, so x over x1 over 4 minus, so this is minus x1 plus x2 over 4, right, is less than minus log of 4 plus log of k. And hence, I can write x1 plus x2 is bigger than, if I multiply with the negative 1, so 4 log of 4 minus log of k, which is a constant. So let's write this as c. And this is my b1. So which implies x1 plus x2 is bigger than equal to c. So this is my c. Okay. So hence we showed that. So therefore, it's clear that the best test of H0 against H1 may be carried out by use of x1 plus x2. You see, that is the thing. Okay. Now here in this particular example, we can even do better. So in fact, for this example, we are done here, but for this example, we know that x1, it follows, it's an exponential distribution. So it follows, basically it follows a gamma 1 over under the null hypothesis. Under h0, it follows theta prime, which is really equal to exponential 1 over theta prime. That is what is given from the probability density function. And x2 is also the same thing. And therefore, we know that x1 plus x2, if they're gamma, it's given by this first parameters alphas are added. So it's 2, 1 over theta prime. Also, we know that gamma of, I think we wrote it last time. So gamma of m over 2, k over 2, sorry, m over 2, 1/2 is same as chi squared of m. Note. So that means this follows for h0, my theta prime is given to be 2. It got to be 2. Yes. Right. The theta prime is 2. So x1 plus x2 really follows gamma of 2 comma 1/2, which is same as chi squared of 4. Right. So if the significance level or size of the critical region is alpha, then what we really want is we want this x1 plus x2. If x1 plus x2 is bigger than, so this c, so why do we choose this c? So I can choose this c to be chi squared with 4 degrees of freedom and 1 minus alpha. Then we can reject h0. That's an aside. You don't have to do it for completing this problem. So in other words, what we said is we can choose this c to be, so that is, let me write. So that is, we can choose c to be chi squared of 4, 1 minus alpha. So that is the point right here. Okay. Okay. One final example, and then we're done. So let's see. This number, one last example. It goes like the following. It goes like, so this is exercise 8.1.3. Repeat the last example when h1 is theta equals to theta double prime equals to 6. And then generalize this for every theta double prime bigger than 2. We'll see the purpose of this in the next chapter, in the next class. Okay. Now here is a solution. We'll mostly build on the analysis that we already developed. In general, we have L of, so we have here L of 2 of L of theta double prime, right? So I'll just keep this 2 and I'll just write theta double prime. Say L of 2 over L of theta double prime is less than equal to K for some K bigger than 0 implies, with the same analysis which we have done earlier, so it's basically here it's 1 over 4 e to the minus x1 plus x2 over 2, 1 over theta double prime squared e to the minus x1 plus x2 over theta double prime less than K, right? So that means we have theta double prime squared over 4, and then we have e to the minus x1 plus x2 over 2, e to the plus x1 plus x2 over theta double prime less than K. Okay, take the log. So we have log of theta double prime squared over 4 minus x1 plus x2 over 2 plus x1 plus x2 over theta double prime is less than log of K, just like before. So I can write this as, if I move this here, so it's minus 1/2, and so it's basically 1 over theta double prime minus 1/2, and then I can write x1 plus x2, right? So I can pull out minus 1/2 here for 1 over theta double prime here and x1 plus x2. Then it's less than log of K minus log of theta double prime squared over 4. Okay. And therefore, I can say that if I mean, usually this theta double prime is bigger than 2. So 1 over theta double prime is less than 1/2. So this quantity here is negative, right? So that means I'll have x1 plus x2 when I multiply by that. So my inequality is changed. 1 over theta double prime minus 2. So that's why this inequality is changed. Log of K minus log of theta double prime squared over 4. Now you can take this theta double prime as 6 for the first example, and you get the exact same. So when theta double prime is bigger than 2, x1 plus x2 is of the form of C, bigger than C, okay? Just like before. So this whole quantity, so suppose that a double prime is 6, so this is a constant, right? So for a given number, of course, this number is dependent on theta double prime. But again, we can make it also independent of theta double prime. We'll talk about this next time by choosing this K, because I have the freedom for choosing this K. I can choose this K dependent on theta double prime so that I can make this whole thing independent of theta double prime. But anyway, today it does not matter. So it's just a constant, okay? So the same analysis. So same analysis of the last example is valid, and hence we can say that well, basically, so the critical region, so the best test is to reject H0 if x1 plus x2 is bigger than chi squared 4 1 minus alpha, with alpha being the size of the critical region, or another way of level of significance, another way of saying the same thing. So we get this for every possible theta bigger than 2. Okay? So true for every theta double prime bigger than 2. Okay, so today, therefore, we learned how we can conduct the base test, and everything that we studied, that is really based on the Neyman-Pearson theorem. And that's a very nice theorem. So what we have seen is how we can compute the best critical region, and what is meant by the best critical region. And then we have seen how we can really implement this for various examples. So if there are more than one critical regions, then the concept of best critical region comes. And consequently, the best test is the one that is using the best critical region. And then we have seen that there are many tests which can be performed like that, and those are the best tests. Okay. And now note that there are more than one tests possible for every case. Okay, so next time we'll be sort of generalizing this concept. Today we have done for two simple hypotheses, maybe theta 0 equals or theta equals to theta prime versus theta equals to theta double prime. But next time we'll be considering the case for theta equals to theta prime versus theta bigger than or less than or maybe not equal to theta prime. Okay, all right, thank you.